Section 8.3 is pretty much the same as Section 8.2, but instead of vectors in 2D, we're going to think about vectors in 3D. I am not going to make you draw a vector or draw anything in 3D, but I do want to show you what a three-dimensional plane looks like. We have an x-axis and a y-axis, and those two are perpendicular to each other. It is a right angle right there. It doesn't look like it, it's just drawn in perspective. And then in addition to an x and a y, so that kind of, if you imagine like you're standing up here and looking down at it, you'd have your x and your y just like you would normally. But in addition, we also have a z-axis, and the z-axis comes out of the plane. So instead of ordered pairs, we're going to have ordered triples, x, y, and z. So they're going to go a certain distance in the x direction, a certain distance in the y direction, and then straight up a certain distance in the z direction. Like I said, I'm not going to ask you to draw things out like that or to locate points, but I do want to show you what it would look like. So if we were trying to find the point -4, 3, 2, in the x direction we'd go backwards 4, 1, 2, 3, 4. In the y direction we'd go forward 3, 1, 2, 3, and then we'd come straight up 2 in the z direction, and there's the ordered pair. I'm not going to ask you to draw it out like that on a test or a quiz, but I do want you to know kind of what it looks like. Alright, what will I ask you to do? I will ask you to do things like example 2 or 3, write an ordered triple that represents a vector that goes from 5, -3, 2, to 4, -5, 6. If I want to write that ordered triple, I need to figure out how much it changes, just like I did with the ordered pairs. So I need to know how much does it change in the x direction when it goes from 5 to 4. It goes backwards 1. How much do I change in the y direction when I go from -3 to -5? Backwards 2. And in the z direction, I'm changing from 2 to 6. So that time I'm going forward 4. The ordered triple would be -1, -2, 4. Now we can also change that into a magnitude of that vector. When we found the magnitude in the last section, we did the Pythagorean theorem, x squared plus y squared equaled magnitude squared. Same sort of thing. To find the magnitude here, instead of just x squared plus y squared, we're going to have x squared plus y squared plus z squared equals the magnitude squared. The Pythagorean theorem does generalize out to 3 dimensions, and you can do x squared plus y squared equals z squared to get the length of that last side. So the magnitude of this vector is the square root of 21. You're going to do those same 2 things, write an ordered triple and find the magnitude on example 3. Example 3 is talking about an application about a bee flying through space. If it passes through the point 0, 3, 3, and then it goes to 5, 0, 4, what's the magnitude of the displacement the bee experienced in traveling between the 2 points? So they're asking you to find the magnitude. I'd like you to do an ordered triple first and then find the magnitude. So let's pause the video and see if you can write an ordered triple for a vector that goes from 0, 3, 3 to 5, 0, 4, and then also find the magnitude of that vector. So after doing x minus x, y minus y, z minus z to figure out the change in all 3 directions, you should get an ordered triple -5, -3, 1. And when you do the Pythagorean theorem, you get a magnitude of the square root of 35. We can also add and subtract vectors in 3D. It's going to work the same way it did in the last section. If we want to do something like 3p, we're going to distribute the 3 to all 3 parts. 2q, the same way, we're going to distribute the 2 to all 3 parts. And then just subtract the vectors. Subtract the x's, subtract the y's, and subtract the z's. So let's see what we would get. 3p is 3 times 3, 0, 4 minus 2q, and q is 2, 1, negative 1. So we'll use order of operations and multiply first. And also multiply on the second one. And then subtract. And be really careful of your negatives when you subtract. That's our answer in vector form. We can also write it as the sum of unit vectors. In 2 dimensions, we had i's and j's. This time we're going to have i's, j's, and k's for the z direction. The I, j, and k is something engineers use a little bit more, and the ordered triple is what you're going to see in our class. But you need to know both for the test. Here's an example looking at the sum of unit vectors again. There's a description of it again. Any vector can be rewritten as the sum of unit vectors, however many x's you need, however many y's you need, plus however many z's you need. You can rewrite any vector as the sum of unit vectors. They want you to write vector AB as the sum of unit vectors if A is here and B is there. I'm going to start by writing it as an ordered triple first, and then change it into the i's, j's, and k's. Pause the video and see if you can do that one on your own. I think we've done examples like that already today, so see if you can figure this one out on your own. On that last one, I wrote plus a negative. You can also write minus instead of plus a negative. And here at the end, if it's 1k, you wouldn't need the 1 there. You could just say negative 6i minus 6j plus k. Either way is fine. And that takes care of section 3. Again, the homework is mostly adding and subtracting vectors. And then you also have to write some of them as the sum of unit vectors.